Introduction: The National Scaling Trilogy. This audiobook is one of a three-part series that examines how nations move from fragmented construction to industrialized, scalable, and economically resilient housing systems. Each book focuses on a different layer of the transformation, and together they form a complete blueprint for national capability building. The first book, OSC, The Market Paradox, explores why the off-site construction market has struggled to scale. It explains how inconsistent language, unstable products, and misaligned expectations prevented OSC from becoming a true industrial sector. That book shows the listener why the market failed to stabilize, and why a more deliberate route to market is required. The second book, OSC, The Technical Engine, introduces the engineering and manufacturing logic needed to stabilize products, standardize components, and create repeatable, interoperable building systems. It explains how engineering discipline replaces variability, and how manufacturing logic replaces artisanal workflows. This third book, the one you are listening to now, The National Housing Production Strategy, takes the final step. It moves from market logic and technical logic into national scaling logic. It explains how EMBS, Quad, and housing production zones combine to create a national industrialized housing system capable of delivering predictable volume, stable economics, and long-term sovereign capability. Together, the trilogy provides a complete route to national industrialization. A market logic: why OSC failed to scale a technical logic, how engineered systems stabilize products and national logic, how EMBS, Quad, and zones create industrial capacity. This audiobook focuses on the national layer. It explains the system architecture, the economic logic, the operational model, and the governance structures required to deliver housing at true national scale. It is written for policymakers, industry leaders, manufacturers, investors, and operators who need a clear, implementable, engineering-led pathway from aspiration to execution. This introduction sets the stage. The chapters that follow provide the system. Preface. This book comes from more than 20 years spent inside the real world of construction, manufacturing, and housing delivery. 2 decades of trying to solve the same structural problems with tools that were never built for the scale of the challenge. No matter the country, the market, or the political cycle, the pattern has been the same: fragmented supply chains, unpredictable delivery, and a system that can't turn policy ambition into industrial capacity. What started as technical frustration eventually became a full systemic diagnosis, and that diagnosis became the foundation for the frameworks in this book, EMBS, Quad, and the wider industrialization architecture that supports them. The purpose of this book isn't to add another opinion to the already crowded conversation about housing. Its purpose is to provide a system, a workable, scalable, nationally deployable system, for delivering homes at the speed, quality, and predictability modern societies require. These frameworks aren't theoretical. They come from lived experience, from factory floors, design offices, construction sites, procurement rooms, and policy environments where decisions collide with constraints. They are built to close the gap between political intent and industrial reality, giving governments and operators a clear path from aspiration to execution. Industrialized housing isn't a trend or a niche. It's a structural necessity. Countries that fail to industrialize will face rising costs, shrinking labor pools, and delivery cycles that can't keep up with demographic and economic pressures. Countries that succeed will build durable capacity, stabilize markets, and create a predictable national pipeline that supports both public objectives and private investment. This book sets out the architecture for that transition: the standards, the zones, the workflows, the governance, and the production logic needed to move from traditional construction to a modern, integrated, repeatable system. Readers should treat this book as a technical manual, a strategic blueprint, and a practical guide. It is intentionally direct. It avoids unnecessary narrative. It focuses on what works, what fails, and what must change. The frameworks are modular, so governments, developers, manufacturers, and financial institutions can adopt them at different levels of maturity. Whether you work in national policy, industrial strategy, factory operations, or project delivery, the principles are the same: integration, standardization, predictability, and scale. This preface is a contract with the reader. The chapters that follow won't offer abstract theory or speculative models. They offer a system, one that can be implemented, measured, and scaled. A system capable of transforming housing from a fragmented craft into a coordinated industrial sector. A system built not on ideology, but on engineering, economics, and operational discipline. A system designed to work in the real world. Introduction. Executive summary. The United Kingdom faces a structural housing delivery failure that cannot be fixed through incremental reform. The system is fragmented, inefficient, and unable to deliver the volume, quality, or consistency the country needs. Decades of policy churn, market volatility, and reliance on artisanal construction have created a delivery environment that is slow, expensive, and fundamentally unscalable. This document sets out a coherent national model for industrialized housing delivery, grounded in engineering logic, manufacturing discipline, and system-level assurance. It introduces the EMBS framework, Engineering-Led Modern Building Systems, the Quad model, which stands for quality, uniformity, assurance, and delivery, and the concept of EMBS zones as the structural backbone of a national housing strategy. This approach is not theoretical. It is based on real-world delivery experience, international benchmarking, and the operational realities of manufacturing-led construction. It provides a practical, scalable, and assured pathway to deliver high-quality homes at national scale. The document is structured to support ministerial decision-making, cross-departmental alignment, and industry adoption. It offers a clear diagnosis of the national problem, a coherent framework for industrialized delivery, and case studies showing how the model performs in practice. Forward. The UK has spent decades trying to modernize construction without ever establishing a stable, engineering-led foundation for doing so. Policy initiatives have come and gone. Funding programs have launched and collapsed. Pilot projects have been celebrated and forgotten. Meanwhile, the underlying system has stayed the same, fragmented, artisanal, and structurally incapable of scaling. This document is written to break that cycle. It is not a policy paper, a consultancy report, or a theoretical exercise. It is a practical blueprint for a national industrialized housing system, one that treats homes as engineered products, not bespoke projects, one that uses manufacturing logic, not artisanal craft, one that delivers consistency, not variability. The frameworks presented here, EMBS, Quad, and EMBS zones, are designed to give government, industry, and investors a stable, predictable, and assured foundation for long-term planning. They are built on engineering principles, not political cycles. They are designed to endure. The UK does not lack talent, ambition, or innovation. It lacks structure. This document provides that structure. Housing challenges to scale. The UK's housing system isn't short of effort, it's short of structure. The real challenge is scale, and the current model simply cannot deliver it. Traditional construction depends on variable materials, variable workmanship, and variable site conditions. It's a system built on prototypes instead of products. That variability, combined with fragmented governance, slow planning, and reactive assurance, creates a delivery environment that cannot meet national demand. The result is a structural deficit that pushes costs up, drags productivity down, and deepens regional inequality. Workforce decline, material volatility, and outdated delivery models make the problem worse, while institutional processes remain slow, risk-averse, and misaligned with the certainty required for industrialized production. Market behavior reinforces scarcity instead of scale, and without a national delivery framework, the system operates as disconnected local projects rather than a coordinated industrial program. This section outlines the systemic constraints, from planning friction and land release to market dynamics and institutional inertia, that prevent the UK from building at pace. It sets the analytical foundation for why the country must shift from a fragmented, reactive, project-led model to a coordinated, engineered, manufacturing-driven system capable of delivering housing at true national scale. National problem definition. 1. A system that cannot scale. The UK's housing delivery system cannot scale to meet national demand. Traditional construction relies on fragmented supply chains, variable workmanship, and site-based processes that cannot achieve manufacturing-level throughput. The result is slow, inconsistent, high-cost delivery. 2. Variability. As a structural weakness, every traditionally built home is effectively a prototype. Materials vary. Workmanship varies. Site conditions vary. Sequencing varies. This variability drives defects, delays, and cost overruns. It also makes assurance difficult because no two units are ever truly identical. 3. Lack of national coordination. Housing delivery is treated as a series of local projects instead of a national industrial program. This creates duplication, inefficiency, and an inability to leverage economies of scale. Without national coordination, the system cannot stabilize demand, standardize components, or support long-term investment in manufacturing capacity. 4. Policy instability. Frequent policy changes undermine confidence and prevent industry from investing in long-term capability. Manufacturers cannot scale without predictable demand. Developers cannot plan without stable regulation. Investors cannot commit without clarity. The system becomes trapped in short-term thinking. 5. Absence of engineering discipline. Construction in the UK is not treated as an engineering discipline. It lacks structured processes, controlled environments, and rigorous assurance frameworks, the hallmarks of mature manufacturing sectors. Without engineering discipline, quality is inconsistent, productivity is low, and risk is high. 6. Fragmented assurance. Assurance is reactive rather than proactive. It relies on inspections, snagging, and post-completion remediation instead of embedded quality control. This approach is incompatible with industrialized delivery and contributes to systemic inefficiency. 7. Workforce constraints. The UK faces a shrinking construction workforce with an aging demographic and limited new entrants. Traditional construction is labor-intensive and heavily reliant on skilled trades. Without industrialization, workforce decline becomes a structural barrier to delivery. 8. Cost instability. Material prices, labor costs, and supply chain volatility create unpredictable delivery environments. Traditional construction amplifies this volatility because it lacks standardization, bulk procurement, and controlled production conditions. 9. Lack of productization. Homes are not treated as products with defined specifications, controlled components, and repeatable processes. Instead, they are treated as bespoke projects. This prevents standardization, blocks innovation, and makes scaling impossible. 10. Failure to leverage manufacturing. The UK has world-class manufacturing capability in aerospace, automotive, and advanced engineering. Almost none of it has been integrated into housing delivery. The system continues to rely on outdated methods while ignoring proven industrial models. Structural drivers of the deficit. 1. Planning system friction. The UK's discretionary, case-by-case planning model creates delay and uncertainty. Local authorities vary widely in interpretation, capacity, and political appetite, which leads to unpredictable outcomes and long approval timelines. 2. Land supply constraints. Land release is shaped more by political risk than strategic need. This creates a persistent mismatch between where demand is highest and where development is actually permitted, reinforcing regional imbalance. 3. Fragmented delivery capacity. The UK depends on a small number of large developers whose business models prioritize controlled, phased release rather than rapid output. This places a structural ceiling on how many homes can be delivered each year. 4. Limited industrial capability. Construction remains largely manual and site-based, with limited adoption of industrialized manufacturing methods. This restricts throughput, consistency, and scalability. 5. Labor market pressures. An aging workforce, declining apprenticeship numbers, and competition from other sectors reduce the available labor pool. This limits the sector's ability to expand production. 6. Infrastructure misalignment. Housing delivery is often disconnected from transport, utilities, and social infrastructure planning. This misalignment delays development and increases cost and complexity. 7. Financial model rigidity. Traditional financing models favor incremental, risk-managed build-out rather than large-scale, rapid deployment. This limits the system's ability to respond to national-level demand. 8. Localized decision-making. Local authorities operate within narrow geographic and political boundaries, making it difficult to coordinate delivery at the scale required to address national shortages. 9. Policy instability. Frequent shifts in national housing policy create uncertainty for investors, developers, and local authorities. This discourages long-term planning and sustained capacity building. 10. Absence of a national delivery framework. The UK lacks a unified, industrial-scale delivery mechanism capable of coordinating land, planning, infrastructure, and manufacturing. Without this, the system cannot close the housing deficit at the pace required. Consequences of the deficit. 1. Rising housing costs. The ongoing shortage pushes prices and rents up faster than wages. Affordability falls, financial pressure increases, and inequality widens. Opportunity becomes concentrated in places where housing is already expensive. 2. Increased homelessness. A constrained housing supply leaves vulnerable groups with few options, driving growth in both visible and hidden homelessness. Local authorities face rising temporary accommodation costs and shrinking capacity to intervene effectively. 3. Labor market distortion. High housing costs restrict labor mobility. Employers struggle to attract and retain workers in high-demand regions. Productivity falls, and the competitiveness of key economic centers is weakened. 4. Regional inequality. The deficit reinforces geographic disparities. Growth concentrates in areas with existing supply, while lower-income households are priced out. Regions with constrained supply face intensified pressure, while others stagnate. 5. Reduced household formation. Younger adults delay forming independent households because of cost barriers. This leads to overcrowding, multi-generational living, and suppressed demand for new homes. The long-term demographic and economic impacts are significant. 6. Public service strain. Local authorities face rising demand for housing support, temporary accommodation, and social services. The deficit increases fiscal pressure and diverts resources away from long-term investment and into short-term crisis management. 7. Economic underperformance. The housing shortage constrains labor supply, reduces productivity, and limits the growth of high-value industries. The national economy operates below potential because housing acts as a structural brake on growth. 8. Social fragmentation. Communities become more polarized as lower-income households are displaced from high-cost areas. Social cohesion weakens, diversity declines, and local networks that support resilience and well-being erode. 9. Declining living standards. Overcrowding, long commutes, and insecure tenure reduce quality of life. Households spend a growing share of income on housing, leaving less for education, health, and long-term savings. 10. Long-term fiscal burden. The deficit increases government spending on housing benefits, temporary accommodation, and emergency interventions. Without structural reform, these costs compound year after year and reduce fiscal flexibility. Systemic barriers to scaling supply. 1. Fragmented governance structure. Housing delivery is split across national departments, regional bodies, and local authorities, each with different priorities and limited coordination. This fragmentation prevents coherent national planning and slows decision-making. 2. Inconsistent policy direction. Frequent changes to housing policy, planning rules, and funding mechanisms create uncertainty for developers, investors, and local authorities. This instability discourages long-term commitments and undermines confidence in scaling. 3. Slow planning determination. Planning decisions often take months or even years because of limited local authority capacity, complex assessments, and political pressures. These delays increase risk, cost, and uncertainty, reducing appetite for large-scale delivery. 4. Infrastructure lag. Transport, utilities, and social infrastructure often lag behind housing proposals. These bottlenecks stall or downsize developments. Without aligned infrastructure investment, supply cannot expand at pace. 5. Land market inefficiency. Land values are inflated by speculative behavior and opaque ownership structures. This distorts viability, limits access to developable land, and encourages slow build-out to maintain price levels. 6. Limited industrialization of construction. The sector is still dominated by traditional, labor-intensive methods with low productivity growth. Without industrialized manufacturing capacity, the system cannot scale to meet national demand. 7. Skills shortages. A shrinking workforce, limited training pathways, and competition from other industries reduce the availability of skilled labor. This constrains output and increases reliance on slower, manual processes. 8. Financial risk aversion. Lenders and investors prefer predictable, phased development models rather than large-scale, rapid deployment. This financial conservatism limits innovation and caps annual delivery volumes. 9. Local political resistance. Local opposition to development, often driven by concerns about character, traffic, or infrastructure, influences planning decisions and restricts supply. This creates a structural drag on delivery. 10. Absence of a national industrial strategy for housing. The UK lacks a coordinated, long-term strategy that integrates land, planning, infrastructure, and manufacturing into a unified delivery system. Without this, scaling remains fragmented and inefficient. Market dynamics reinforcing the deficit. 1. Price-driven land behavior. Landowners often hold sites to maximize future value instead of releasing them for development. This speculative behavior restricts supply, inflates land prices, and reinforces the structural imbalance between demand and delivery. 2. Developer build-out strategies. Large developers phase construction to maintain price stability and protect margins. This controlled release model limits annual output and prevents the market from responding to national-level demand. 3. High cost of capital. Rising interest rates and tighter lending criteria increase the cost of development finance. This reduces viability, especially for complex or marginal sites, and slows the pace of new starts. 4. Concentrated market power. A small number of major developers dominate the market, shaping supply patterns and influencing pricing. Limited competition reduces innovation and reinforces slow, incremental delivery models. 5. Volatile material prices. Global supply chain fluctuations create unpredictable material costs. This undermines viability, discourages long-term planning, and increases risk, slowing investment decisions. 6. Limited SME participation. Small and medium-sized builders face barriers in accessing land, finance, and planning approvals. Their declining market share reduces diversity, resilience, and overall system capacity. 7. Investor preference for stability. Institutional investors favor predictable, low-risk returns, often prioritizing rental assets over large-scale development. This shapes market behavior and limits capital available for rapid expansion. 8. Demand outpacing supply. Population growth, household formation, and migration continue to increase demand faster than supply can respond. This persistent imbalance drives price escalation and deepens the deficit. 9. Limited innovation incentives. The market rewards predictable delivery models rather than innovation. Without incentives or competitive pressure, new technologies and industrialized methods struggle to gain traction. 10. Rental market tightening. Insufficient rental supply increases competition for available homes, driving up rents and reducing mobility. This further constrains households and amplifies affordability pressures. Institutional constraints limiting reform. 1. Fragmented policy ownership. Housing responsibilities are spread across multiple government departments, each with different mandates and priorities. This fragmentation prevents a unified strategy, slows reform, and creates overlapping or even contradictory interventions. 2. Limited local authority capacity. Many local authorities lack the staff, expertise, and resources needed to manage complex planning, viability, and infrastructure processes. This capacity gap slows approvals and reduces the system's ability to scale delivery. 3. Short political cycles. Frequent changes in leadership and policy direction disrupt long-term planning. Housing reform requires multi-decade continuity, but political cycles incentivize short-term decisions that undermine structural progress. 4. Regulatory complexity. The regulatory environment is dense, overlapping, and inconsistent across regions. Navigating these layers increases cost, risk, and delay, discouraging innovation and large-scale development. 5. Slow institutional decision-making. Major decisions involving land, infrastructure, and funding often require multi-agency approval. These processes are slow, risk-averse, and prone to delay, limiting the pace at which reforms can be implemented. 6. Weak data and forecasting systems. National and local bodies often rely on outdated or inconsistent data to plan housing needs. This undermines strategic planning, misallocates resources, and reduces the accuracy of long-term projections. 7. Limited accountability mechanisms. No single institution is accountable for national housing outcomes. Without clear responsibility, failures persist without consequence, and reform efforts lose momentum. 8. Funding constraints. Public bodies face tight budgets that limit their ability to invest in planning capacity, infrastructure, and land assembly. These constraints slow development and reduce the effectiveness of policy interventions. 9. Resistance to structural change. Institutions often favor established processes and are cautious about adopting new delivery models. This cultural inertia slows the adoption of industrialized construction, digital planning, and modern land strategies. 10. Absence of a national delivery mandate. No central body has the authority to coordinate land, planning, infrastructure, and manufacturing at scale. Without a national delivery mandate, systemic reform remains fragmented and slow. Structural barriers to housing system reform. 1. Fragmented governance. The housing system is constrained by authority spread across ministries, agencies, and local jurisdictions. This dispersal slows coordination, creates inconsistent standards, and limits the ability to execute reform at national scale. 2. Planning system rigidity. Legacy planning frameworks were designed for incremental growth, not rapid, industrialized delivery. Slow and unpredictable approval cycles undermine investment confidence and delay large-scale programs. 3. Land release constraints. Strategic land is often locked behind slow release mechanisms, speculative holding, or fragmented ownership. This restricts the ability to assemble sites at the scale required for industrialized housing programs. 4. Infrastructure lag. Transport, utilities, and social infrastructure frequently fall behind housing demand. These delays create bottlenecks that restrict viable development zones and slow delivery. 5. Procurement limitations. Traditional procurement models prioritize lowest upfront cost rather than long-term value. This discourages innovation and industrialized methods that depend on pipeline certainty. 6. Skills and workforce gaps. The construction workforce is aging and not sufficiently trained in modern methods. This limits the sector's ability to transition toward higher productivity, industrialized systems. 7. financial system friction. Conventional financing structures favor short-term returns and traditional delivery models. These incentives are misaligned with the capital requirements and certainty needed for industrialized housing. 8. Market concentration. A small number of dominant developers shape supply, pricing, and land strategy. This reduces competitive pressure and limits innovation across the sector. 9. Regulatory inertia. Building regulations and compliance pathways remain optimized for traditional construction. This creates duplicated testing, inconsistent interpretation, and barriers for industrialized systems. 10. Data and transparency gaps. The system lacks unified, reliable, real-time data on demand, supply, land, productivity, and performance. These gaps limit evidence-based policymaking and slow structural reform. Strategic levers for system transformation. 1. National policy alignment. Coherent national policy provides the clarity and stability needed for long-term investment. It allows government, industry, and finance to operate against a shared set of priorities and measurable outcomes. 2. Planning system modernization. Streamlining approvals, standardizing processes, and creating predictable pathways for industrialized methods reduces systemic delay and strengthens the reliability of development pipelines. 3. Land strategy reform. Coordinated land identification, assembly, and release, supported by transparent criteria and long-term zoning certainty, creates the conditions for large-scale, manufacturing-led delivery. 4. Infrastructure synchronization. Aligning transport, utilities, and social infrastructure planning with housing demand ensures development zones are viable, connected, and capable of supporting accelerated delivery. 5. Industrialized procurement models. Shifting procurement from lowest-cost tendering to value-driven, pipeline-based framework supports manufacturing investment, innovation, and long-term productivity gains. 6. Skills and workforce transition. Targeted training, accreditation, and workforce development programs enable the sector to shift from labor-intensive traditional methods to higher productivity industrialized systems. 7. Financial innovation and incentives. New financing mechanisms, such as outcome-based funding, pipeline guarantees, and manufacturing-aligned investment structures, unlock capital for industrialized housing at scale. 8. Market diversification. Encouraging new entrants, alternative delivery models, and competitive manufacturing ecosystems reduces dependency on traditional developers and increases system resilience. 9. Regulatory modernization. Updating building regulations, certification pathways, and compliance processes to reflect industrialized methods removes duplicated testing and accelerates safe adoption. 10. Data-driven governance. A unified national data framework provides real-time insight into demand, supply, productivity, land, and performance. This supports evidence-based decision-making and targeted intervention. Industrial zones, national foundation of right and left-hand collaboration. Industrial zones act as the structural bridge between the two halves of the national housing system, the policy-driven right hand of government and the market-driven left hand of enterprise. Today, these two forces operate in parallel but rarely in synchrony. The result is fragmented land decisions, inconsistent planning outcomes, unstable pipelines, and a delivery environment defined more by variability than by national intent. Industrial zones resolve this by creating a single, coordinated platform where land, planning, infrastructure, manufacturing, logistics, and compliance are aligned under one controlled operating model. As the document states, industrial zones provide a structured national framework that aligns land, planning, infrastructure, and delivery capacity, and bring together the actors required for industrialized housing into a coordinated delivery environment with shared objectives. By consolidating authority, standardizing pathways, and embedding assurance, zones replace discretionary interpretation with predictable rules. They stabilize supply chains, concentrate skills, and create the long-term demand visibility manufacturers need to invest in capacity, automation, and innovation. They also ensure that infrastructure, transport, utilities, and digital networks is delivered in parallel with housing need rather than lagging behind it, addressing one of the most persistent structural failures in traditional delivery models. As the document reinforces, zones ensure that transport, utilities, and digital infrastructure are planned and delivered in parallel with housing demand. Most importantly, industrial zones create the national conditions for throughput. They transform housing from a fragmented, project-by-project activity into a coordinated industrial system capable of sustained, high-volume output. They provide the governance, compliance stability, and operational control required for a modernized housing economy, one where the right hand sets national objectives and the left hand delivers against them with precision, repeatability, and scale. In doing so, zones become the mechanism through which a nation finally aligns intent with capability and policy with production. Purpose of industrial zones. 1. National coordination. Industrial zones create a structured national framework that aligns land, planning, infrastructure, and delivery capacity. They establish predictable conditions for large-scale housing programs and reduce fragmentation across regions. 2. Strategic land organization. Zones enable the coordinated identification, assembly, and preparation of land. This ensures development happens in locations that support national housing need rather than in opportunistic or speculative patterns. 3. Manufacturing integration. Industrial zones create the conditions for manufacturing-led delivery by aligning factory capacity, logistics routes, and site readiness. This integration reduces variability and supports high-throughput production. 4. Infrastructure alignment. Zones ensure that transport, utilities, and digital infrastructure are planned and delivered in parallel with housing demand. This reduces bottlenecks and increases the viability of large-scale development. 5. Delivery consolidation. They bring together the actors required for industrialized housing, manufacturers, developers, logistics providers, and local authorities, into a coordinated delivery environment with shared objectives and predictable workflows. 6. Assurance and compliance. Stability. Industrial zones support consistent regulatory interpretation and streamlined compliance pathways. This reduces delay, increases predictability, and supports the adoption of modern, industrialized methods. 7. Workforce and skills concentration. Zones allow workforce development, training, and skills programs to be aligned with manufacturing and delivery needs. This supports productivity and reduces reliance on dispersed artisanal labor. 8. Economic efficiency. By concentrating demand, infrastructure, and production, industrial zones enable economies of scale, reduce unit costs, and stabilize supply chains. This creates a more resilient and efficient national delivery system. 9. Pipeline certainty. Zones provide long-term visibility of demand, enabling manufacturers and investors to commit to capacity expansion, automation, and innovation. This certainty is essential for industrialized housing to scale. 10. National throughput enablement. Industrial zones form the foundational platform for increasing national housing throughput. They create the structural environment in which high-volume, repeatable, assured delivery becomes possible. Functions of industrial zones. 1. Land identification and allocation. Industrial zones create a structured mechanism for identifying, prioritizing, and allocating land suitable for large-scale housing delivery. They ensure land supply aligns with national demand rather than fragmented local decisions. 2. Planning streamlining. Zones establish predictable planning pathways by standardizing requirements, reducing discretionary interpretation, and accelerating approvals. This increases certainty for manufacturers, developers, and investors. 3. Infrastructure coordination. Zones coordinate transport, utilities, and digital infrastructure so development sites are viable, serviced, and ready for accelerated deployment. This reduces bottlenecks and prevents avoidable delays. 4. Manufacturing and logistics integration. Industrial zones align factory capacity, logistics routes, and site operations. This ensures production, transport, and assembly function as a single, coherent system rather than disconnected activities. 5. Delivery management. Zones provide a structured environment for managing throughput, sequencing, and site readiness. They support predictable workflows and reduce variability across projects. 6. Assurance and compliance. Control. Zones enable consistent regulatory interpretation, standardized compliance pathways, and embedded quality assurance. This reduces risk and increases confidence in industrialized delivery. 7. Skills and workforce deployment. Zones support targeted workforce development, training, and deployment aligned with manufacturing and site needs. This concentrates capability and reduces reliance on dispersed artisanal labor. 8. Supply chain stabilization. By consolidating demand and providing predictable pipelines, zones stabilize supply chains, reduce volatility, and support long-term investment in materials, components, and logistics. 9. Economic and productivity. Uplift. Industrial zones generate local and regional economic benefits by concentrating manufacturing, logistics, and delivery activity. They support productivity gains and create high-value employment clusters. 10. National throughput coordination. Zones act as the operational mechanism through which national housing throughput is planned, managed, and scaled. They provide the structural foundation for sustained high-volume delivery. Components of industrial zones. 1. Land framework. A structured land framework defines boundaries, permitted uses, density expectations, and long-term development certainty. This gives clarity for planning, investment, and manufacturing alignment. 2. planning pathways standardized. Predictable planning pathways reduce discretionary interpretation and accelerate approvals. These pathways ensure consistent treatment of industrialized housing systems across regions. 3. Infrastructure platform integrated transport, utilities, digital networks, and logistics capacity support high-volume delivery. This platform ensures sites are viable, serviced, and capable of supporting accelerated deployment. 4. Manufacturing interfaces. Defined interfaces link factories, logistics hubs, and development sites. These interfaces ensure production, transport, and assembly operate as a coordinated, repeatable system. 5. Delivery management systems. Operational systems manage sequencing, throughput, site readiness, and coordination across multiple actors. These systems reduce variability and support predictable delivery. 6. Assurance and compliance framework. A unified assurance environment standardizes compliance, testing, and regulatory interpretation. This reduces delay, increases confidence, and supports industrialized methods. 7. Skills and workforce infrastructure. Training centers, accreditation pathways, and workforce deployment mechanisms are aligned with manufacturing and site requirements. This ensures capability is concentrated where it is needed. 8. Supply chain architecture. A coordinated supply chain structure stabilizes materials, components, and logistics. This architecture supports economies of scale and reduces volatility. 9. Digital coordination environment. Shared digital platforms support planning, sequencing, assurance, and performance monitoring. This environment enables real-time coordination and evidence-based decision-making. 10. Governance and control mechanisms. Clear governance structures define roles, responsibilities, escalation routes, and accountability. These mechanisms ensure zones operate as controlled, high-performance delivery environments. Operating model of industrial zones. 1. Zone governance structure. A defined governance body coordinates land, planning, infrastructure, manufacturing, and delivery. This structure provides clear accountability and consistent decision-making across all zone activities. 2. Planning and approvals workflow. A streamlined approvals process with standardized requirements, predictable timelines, and reduced discretionary interpretation. This workflow gives manufacturers, developers, and investors the certainty they need. 3. Infrastructure delivery mechanism. A coordinated mechanism sequences transport, utilities, and digital infrastructure alongside housing delivery. This ensures sites are serviced, viable, and capable of supporting accelerated deployment. 4. Manufacturing coordination model. A structured interface links factories, logistics hubs, and development sites. This model synchronizes production, transport, and assembly to maintain throughput and reduce variability. 5. Logistics and transport operations. Integrated logistics planning aligns factory output with transport capacity, site access, and installation sequencing. This reduces bottlenecks and supports predictable delivery. 6. Assurance and compliance operations. A unified assurance environment embeds quality control, standardized testing, and consistent regulatory interpretation. This reduces risk and accelerates the adoption of industrialized methods. 7. Workforce deployment system. A coordinated system trains, certifies, and deploys skilled labor across manufacturing and site operations. This ensures capability is available where and when it is needed. 8. Supply chain management framework. A framework stabilizes material flows, component availability, and logistics capacity. This supports economies of scale and reduces exposure to market volatility. 9. Digital coordination platform. A shared digital environment supports planning, sequencing, assurance, and performance monitoring. This platform enables real-time coordination and evidence-based decision-making. 10. Performance and throughput control. A system monitors output, identifies bottlenecks, and adjusts workflows to maintain throughput. This ensures zones operate as controlled, high-performance delivery environments. Performance requirements of industrial zones. 1. Throughput capacity zones must sustain predictable, high-volume output aligned with national housing demand. This requires coordinated manufacturing, logistics, and site operations capable of maintaining continuous flow. 2. Planning predictability approvals must be delivered within defined timeframes with minimal discretionary variation. Predictability allows manufacturers and investors to commit to long-term capacity expansion. 3. Infrastructure readiness. Transport, utilities, and digital networks must be in place ahead of deployment. Infrastructure readiness ensures sites are viable and prevents bottlenecks that disrupt throughput. 4. Manufacturing reliability. Factories must operate with consistent output, controlled processes, and stable supply chains. Reliability underpins the repeatability required for industrialized delivery. 5. Logistics efficiency. Transport operations must synchronize with factory production and site sequencing. Efficient logistics reduce delays, minimize handling, and support continuous installation. 6. Assurance consistency. Quality assurance must be embedded, standardized, and consistently interpreted. This ensures compliance is predictable and reduces rework, risk, and delay. 7. Workforce availability. Zones must maintain a trained, accredited workforce aligned with manufacturing and site needs. Workforce availability supports productivity and reduces dependency on artisanal labor. 8. Supply chain stability. Material and component flows must be reliable, scalable, and resilient to market volatility. Stability enables long-term planning and reduces cost variability. 9. Digital integration. Zones must operate on shared digital platforms that coordinate planning, sequencing, assurance, and performance monitoring. Integration enables real-time control and evidence-based decisions. 10. Governance accountability. Clear accountability mechanisms must define responsibilities, escalation routes, and performance oversight. Strong governance ensures zones operate as controlled, high-performance systems. Governance requirements of industrial zones. 1. Clear authority structure. Zones must operate under a defined authority with legal, operational, and strategic responsibility. This ensures decisions are consistent, timely, and aligned with national objectives. 2. Transparent decision-making. Governance must provide clear criteria, publish processes, and predictable outcomes. Transparency reduces uncertainty and strengthens confidence for investors and manufacturers. 3. Regulatory alignment. Zones must align planning, building control, infrastructure regulation, and assurance pathways. This alignment reduces fragmentation and accelerates delivery. 4. Performance oversight. Governance must monitor throughput, quality, compliance, and infrastructure readiness. Oversight ensures zones operate as controlled, high-performance environments. 5. Risk management framework. A structured framework must identify, assess, and mitigate risks across manufacturing, logistics, planning, and delivery. This reduces disruption and maintains continuity. 6. Stakeholder coordination. Governance must coordinate manufacturers, developers, local authorities, infrastructure providers, and regulators. Coordination aligns objectives and reduces operational friction. 7. Compliance assurance. Zones must maintain consistent interpretation of standards, testing requirements, and regulatory obligations. Assurance stability supports industrialized methods and reduces rework. 8. Financial accountability. Governance must ensure transparent budgeting, funding allocation, and financial reporting. Accountability builds trust and enables long-term investment. 9. Data and reporting requirements. Zones must collect, analyze, and report performance data. This enables evidence-based decisions and continuous improvement. 10. Escalation and resolution mechanisms. Clear escalation routes and resolution processes must be in place to address delays, conflicts, or performance issues. This ensures continuity and protects throughput. Compliance requirements of industrial zones. 1. Regulatory consistency. Zones must apply regulations consistently across planning, building control, infrastructure, and assurance. Consistency reduces uncertainty and supports predictable industrialized delivery. 2. Standardized technical requirements. Technical standards must be clearly defined, published, and uniformly interpreted. Standardization ensures manufacturers and developers can design and deliver with confidence. 3. Assurance integration. Assurance processes must be embedded within manufacturing, logistics, and site operations. Integration reduces duplication, accelerates approvals, and maintains quality. 4. Documentation and evidence control. Zones must maintain structured documentation, traceability, and evidence records for all compliance activities. This supports transparency, auditability, and regulatory confidence. 5. Inspection and verification protocols. Clear inspection protocols must define what is checked, when it is checked, and by whom. Verification must be consistent, timely, and aligned with industrialized workflows. 6. Quality management requirements. Zones must operate under defined quality management systems that ensure repeatability, defect reduction, and continuous improvement across all delivery stages. 7. Health and safety compliance. Health and safety standards must be embedded across manufacturing, logistics, and site operations. Compliance ensures safe working environments and reduces operational risk. 8. environmental obligation zones must meet environmental requirements relating to emissions, waste, materials, and land use. Compliance supports sustainability and long-term operational viability. 9. Data and reporting compliance zones must collect, manage, and report data in line with regulatory and governance requirements. Accurate reporting supports oversight and performance management. 10. Continuous compliance monitoring. Compliance must be monitored continuously through digital systems, inspections, and performance reviews. Continuous monitoring ensures issues are identified early and resolved quickly. Operational requirements of industrial zones. 1. Defined operational scope. Zones must operate within a clearly defined scope covering manufacturing, logistics, assembly, and site interface activities. Scope clarity ensures predictable operations and reduces overlap with external authorities. 2. Process standardization. Operational processes must be standardized across manufacturers, logistics providers, and site operators. Standardization supports repeatability, throughput, and consistent quality. 3. Capacity management. Zones must manage production, storage, and logistics capacity to maintain flow and avoid bottlenecks. Effective capacity planning ensures stable throughput and reliable delivery. 4. Scheduling and coordination. Operations must be scheduled and coordinated across manufacturing, transport, and site activities. Coordination reduces delays and supports just-in-time delivery. 5. Resource allocation. Zones must allocate labor, equipment, and infrastructure resources efficiently. Effective allocation supports productivity and operational resilience. 6. Operational monitoring. Zones must monitor production rates, logistics performance, and site interface readiness. Monitoring enables early identification of issues and supports continuous improvement. 7. Maintenance and asset management. Zones must maintain equipment, infrastructure, and digital systems to ensure operational continuity. Strong asset management reduces downtime and protects throughput. 8. Operational safety requirements. Safety protocols must be embedded across all operational activities. Safety compliance protects workers, reduces incidents, and maintains operational stability. 9. Digital integration. Zones must integrate digital systems for scheduling, tracking, assurance, and reporting. Digital integration improves accuracy, transparency, and operational control. 10. Contingency and continuity planning. Zones must maintain contingency plans for disruptions in manufacturing, logistics, or site operations. Continuity planning ensures resilience and protects throughput. Performance requirements of industrial zones. 1. Defined performance metric. Zones must operate against a clear set of performance metrics covering throughput, quality, safety, logistics efficiency, and site interface readiness. Defined metrics ensure transparency and accountability. 2. Productivity benchmark. Zones must maintain productivity benchmarks aligned with industrialized manufacturing and logistics expectations. Benchmarks support continuous improvement and predictable delivery. 3. Quality performance targets. Zones must meet quality targets relating to defect rates, rework, and compliance outcomes. Strong quality performance ensures reliability and reduces downstream risk. 4. Logistics and flow efficiency. Zones must achieve efficient flow of materials, components, and finished assemblies. Flow efficiency supports just-in-time delivery and reduces storage requirements. 5. Schedule adherence. Zones must maintain adherence to production, transport, and site interface schedules. Schedule performance ensures predictability and supports coordinated delivery. 6. Operational reliability. Zones must demonstrate reliable operations with minimal downtime, disruption, or variance. Reliability protects throughput and delivery certainty. 7. Safety performance. Zones must meet safety indicators relating to incidents, near misses, and compliance. Strong safety performance supports stable operations and workforce well-being. 8. Environmental performance. Zones must meet environmental targets relating to emissions, waste, materials efficiency, and resource use. Environmental performance supports sustainability and regulatory compliance. 9. Digital performance reporting. Zones must report performance digitally through structured dashboards, data feeds, and audit trails. Digital reporting enables oversight, transparency, and real-time decision-making. 10. Continuous improvement requirements. Zones must maintain continuous improvement processes to enhance productivity, quality, safety, and flow. Improvement cycles ensure long-term competitiveness and operational excellence. Assurance requirements of industrial zones. 1. Assurance framework zones must operate within a defined assurance framework covering quality, compliance, safety, and performance. The framework provides structured oversight and consistent verification. 2. Independent verification zones must undergo independent verification of processes, outputs, and compliance. Independent oversight strengthens trust, transparency, and regulatory confidence. 3. Quality assurance processes zones must maintain structured quality assurance processes, including inspections, testing, and documentation. These processes protect product integrity and reduce downstream risk. 4. Compliance auditing zones must be subject to regular compliance audits covering regulatory, operational, and environmental requirements. Audits ensure adherence to standards and identify areas for improvement. 5. Digital assurance record zones must maintain digital assurance records that provide traceability, audit trails, and evidence of compliance. Digital records support transparency and efficient oversight. 6. Performance validation zones must validate performance against defined metrics, benchmarks, and contractual requirements. Validation ensures delivery reliability and operational consistency. 7. Safety assurance zones must maintain safety assurance processes that verify adherence to safety protocols, incident reporting, and corrective actions. Safety assurance protects workers and stabilizes operations. 8. Environmental assurance zones must demonstrate compliance with environmental standards through monitoring, reporting, and verification. Environmental assurance supports sustainability and regulatory alignment. 9. Continuous assurance improvement zones must maintain continuous improvement processes within the assurance function to enhance quality, compliance, and reliability. Improvement cycles strengthen long-term performance. 10. Assurance governance zones must operate under a defined assurance governance structure with clear roles, responsibilities, and escalation pathways. Governance ensures accountability and consistent oversight. Reporting requirements of industrial zones. 1. Structured reporting framework zones must operate within a structured reporting framework covering operational, performance, safety, environmental, and compliance data. The framework ensures consistency and comparability across all zones. 2. Mandatory reporting categories zones must report against defined categories including throughput, quality, logistics performance, workforce data, incidents, and environmental metrics. Mandatory categories ensure comprehensive oversight. 3. Reporting frequency zones must submit reports at defined intervals, including daily operational summaries, weekly performance updates, and monthly compliance reports. Regular reporting supports timely decision-making. 4. Digital reporting systems zones must use digital systems for data capture, reporting, and audit trails. Digital reporting improves accuracy, transparency, and traceability. 5. Data quality requirements zones must ensure data accuracy, completeness, and consistency. High-quality data underpins reliable oversight and informed decision-making. 6. Exception and incident reporting zones must report operational exceptions, delays, incidents, and non-conformances promptly. Exception reporting supports rapid response and corrective action. 7. Environmental reporting zones must report environmental performance including emissions, waste, materials usage, and resource efficiency. Environmental reporting supports regulatory compliance and sustainability objectives. 8. Safety reporting zones must report safety incidents, near misses, corrective actions, and compliance with safety protocols. Safety reporting strengthens operational stability and workforce protection. 9. Performance dashboard zones must maintain digital dashboards presenting real-time performance indicators. Dashboards support oversight, transparency, and operational control. 10. Governance reporting zones must provide governance-level reports summarizing performance, risks, compliance status, and improvement actions. Governance reporting ensures accountability and strategic alignment. Enforcement requirements of industrial zones. 1. Enforcement framework zones must operate under a defined enforcement framework that sets out the mechanisms, powers, and procedures for ensuring compliance with operational, safety, environmental, and performance requirements. 2. Regulatory powers authorities must hold clear regulatory powers to inspect, investigate, sanction, and direct corrective actions. Defined powers ensure consistent and enforceable oversight. 3. Inspection protocols zones must be subject to scheduled and unscheduled inspections covering operations, safety, quality, and environmental performance. Inspection protocols ensure transparency and early detection of non-compliance. 4. Non-compliance classification. Non-compliance must be classified by severity, impact, and risk. Classification supports proportionate enforcement and prioritization of corrective actions. 5. Corrective action requirements. Zones must implement corrective actions within defined timeframes. These requirements ensure timely resolution of issues and prevent recurrence. 6. Sanctions and penalties. Authorities must apply sanctions, penalties, or operational restrictions where required. Proportionate enforcement maintains standards and protects delivery outcomes. 7. Escalation procedures. Zones must follow defined escalation pathways for unresolved or serious non-compliance. Escalation ensures accountability and timely intervention. 8. Suspension and revocation powers. Authorities must retain the ability to suspend or revoke zone accreditation or operational permissions in cases of persistent or critical non-compliance. 9. Enforcement. Reporting. Enforcement actions must be recorded and reported through digital systems, providing traceability, transparency, and governance oversight. 10. Continuous enforcement. Improvement. Enforcement processes must be reviewed and improved regularly to strengthen effectiveness, consistency, and alignment with evolving standards. Accreditation requirements of industrial zones. 1. Accreditation framework. Zones must operate within a defined accreditation framework that sets out eligibility criteria, assessment processes, renewal cycles, and the conditions required to maintain accredited status. 2. Eligibility criteria. Zones must meet eligibility criteria relating to governance, capability, infrastructure, safety, environmental management, and operational readiness before accreditation can be granted. 3. Assessment procedures. Zones must undergo structured assessments including documentation review, site inspections, capability evaluation, and performance verification. Assessment ensures readiness and compliance. 4. Accreditation levels. Zones may be accredited at different levels based on capability, maturity, and performance. Tiered accreditation supports transparency and encourages continuous improvement. 5. Accreditation conditions. Zones must comply with defined conditions relating to operations, reporting, safety, environmental performance, and assurance. These conditions ensure ongoing alignment with required standards. 6. Renewal requirements. Zones must renew accreditation at defined intervals through reassessment of capability, performance, and compliance. Renewal maintains confidence in zone operations. 7. Suspension criteria. Accreditation may be suspended where significant non-compliance, safety risks, or operational failures occur. Suspension protects delivery outcomes and public confidence. 8. Revocation criteria. Accreditation may be revoked where persistent or critical failures undermine a zone's ability to operate safely or effectively. Revocation ensures standards are upheld. 9. Accreditation record. Zones must maintain digital records of accreditation status, assessments, conditions, and corrective actions. These records support transparency and governance oversight. 10. Continuous accreditation improvement. Accreditation processes must be reviewed and improved regularly to strengthen consistency, rigor, and alignment with evolving standards. Review and improvement requirements of industrial zones. 1. Review framework. Zones must operate within a structured review framework that defines how performance, compliance, capability, and governance are periodically assessed. The framework ensures consistency and long-term oversight. 2. Periodic review cycle. Zones must undergo scheduled reviews at defined intervals covering operational, safety, environmental, and assurance functions. Review cycles maintain accountability and continuous alignment with standards. 3. Capability reassessment. Zones must be reassessed for capability, capacity, and readiness as part of ongoing improvement. Reassessment ensures zones remain fit for purpose as requirements evolve. 4. Performance trend analysis. Zones must analyze performance trends across throughput, quality, safety, logistics, and environmental indicators. Trend analysis supports early identification of risks and improvement opportunities. 5. Risk review. Zones must conduct structured risk reviews to identify emerging risks, assess controls, and update mitigation plans. Risk reviews strengthen resilience and operational stability. 6. Stakeholder feedback. Zones must gather feedback from manufacturers, logistics providers, site operators, regulators, and workforce representatives. Feedback supports balanced improvement and informed decision-making. 7. Corrective and preventive actions. Zones must implement corrective and preventive actions arising from reviews, audits, incidents, or performance deviations. These actions ensure issues are resolved and prevented from recurring. 8. Improvement planning. Zones must maintain structured improvement plans outlining priorities, timelines, responsibilities, and expected outcomes. Improvement planning supports strategic development and operational excellence. 9. Governance oversight of improvement activities must be overseen by governance bodies to ensure alignment with standards, accountability, and effective implementation. 10. Continuous improvement culture zones must foster a culture of continuous improvement across all functions, encouraging innovation, learning, and proactive enhancement of transition requirements for industrial zones. 1. Transition framework zones must operate within a defined transition framework that sets out how changes in standards, capability, capacity, or regulatory requirements are implemented. The framework ensures orderly, predictable transitions. 2. Change impact assessment zones must assess the operational, financial, safety, and environmental impacts of proposed changes. Impact assessment supports informed decision-making and risk mitigation. 3. Transition planning zones must develop structured transition plans outlining required actions, timelines, responsibilities, and dependencies. Planning ensures coordinated and controlled implementation. 4. Stakeholder coordination zones must coordinate transitions with manufacturers, logistics providers, site operators, regulators, and workforce representatives. Coordination supports alignment and reduces disruption. 5. Capability adjustment zones must adjust capability, processes, or infrastructure where required to meet new standards or operational expectations. Capability adjustment ensures readiness and compliance. 6. Training and workforce preparation zones must provide training and guidance to ensure the workforce is prepared for new processes, systems, or requirements. Workforce preparation supports safe and effective transitions. 7. Digital system updates zones must update digital systems, data structures, and reporting tools to reflect new requirements. Digital updates ensure continuity of assurance, reporting, and oversight. 8. Operational continuity zones must maintain operational continuity during transitions, minimizing disruption to production, logistics, and site interface activities. Continuity protects delivery outcomes. 9. Monitoring of transition progress zones must monitor progress against transition plans, identifying delays, risks, or deviations. Monitoring supports timely corrective action and governance visibility. 10. Post-transition review zones must conduct a post-transition review to evaluate effectiveness, identify lessons learned, and confirm alignment with new requirements. Review strengthens future transitions and continuous improvement. Integration requirements for industrial zones. 1. Integration framework zones must operate within a defined integration framework that governs how systems, processes, data, and stakeholders interconnect. The framework ensures coherence, interoperability, and predictable operational behavior. 2. Interzone coordination zones must coordinate with other industrial zones, logistics hubs, and regional production centers to support national supply chain efficiency and balance capacity utilization. 3. Supply chain integration zones must integrate with upstream suppliers and downstream delivery partners to ensure material flow, production continuity, and alignment with demand schedules. 4. Digital systems interoperability zones must ensure interoperability between digital systems, including production data, quality records, logistics tracking, and compliance reporting. Interoperability supports transparency and national-level oversight. 5. Standards alignment zones must align operational, technical, and quality standards with national frameworks to ensure consistency, comparability, and regulatory compliance across all participating zones. 6. Interface management zones must manage interfaces between manufacturers, logistics providers, site operators, and regulatory bodies. Effective interface management reduces friction, delays, and operational risk. 7. Data sharing requirements zones must share defined datasets with national authorities and supply chain partners to support assurance, forecasting, and performance monitoring. Data sharing must follow agreed protocols and security requirements. 8. Workforce and training integration zones must integrate with regional training providers, vocational institutions, and workforce development programs to ensure a consistent pipeline of skilled labor aligned with zone requirements. 9. Regulatory integration zones must integrate regulatory processes into operational workflows, ensuring that compliance checks, approvals, and reporting are embedded rather than treated as external or optional activities. 10. Continuous integration review zones must conduct periodic reviews of integration performance, identifying gaps, inefficiencies, or misalignments. Continuous review supports improvement and national system coherence. Housing Production Zone, HPZ. The housing production zone represents the structural pivot in the national housing strategy. It is the moment where the system stops treating housing as a scattered, reactive activity and begins treating it as a dedicated industrial operation with its own geography, governance, and production logic. The HPZ is not a policy idea. It is a physical, operational, and economic zone designed specifically for the mass production, assembly, and deployment of housing at national scale. It is the point where the country transitions from building projects to running a housing industry. 1. Purpose of the housing production zone. The HPZ exists to create the conditions necessary for continuous, high-volume, high-quality housing output. Its purpose is to establish a dedicated industrial environment where housing is produced with the same discipline as automotive or aerospace manufacturing. Concentrate supply chains, labor, logistics, and regulatory processes into a single, integrated ecosystem. Remove the fragmentation, duplication, and inefficiency that currently define the construction sector. Provide a stable, predictable production base capable of delivering national housing requirements year after year. The HPZ is the first time the system acknowledges that housing is not a construction problem, it is a production problem. 2. What the HPZ actually is. The HPZ is a geographically defined zone with a dedicated land for factories, assembly lines, logistics yards, testing facilities, and workforce infrastructure. Integrated supply chains located within or adjacent to the zone to eliminate transport delays and dependency risks. A unified regulatory authority that replaces the fragmented approval processes that slow down traditional construction. Industrial-grade utilities and infrastructure designed for continuous operation, not project-based peaks and troughs. A workforce ecosystem including training centers, certification pathways, and stable employment structures. It is not a business park. It is not a cluster. It is not a construction hub. It is a national production asset. 3. Why the HPZ is the turning point. Before the HPZ, the system still operates under the logic of traditional construction, fragmented, site-based, slow, and dependent on temporary labor. After the HPZ, the system shifts to industrialized production, repeatable processes, controlled environments, predictable output, scalable capacity, and national-level coordination. This is the moment where the country stops building houses and starts producing housing. The HPZ is enabled by the system frameworks ENBS, EMBS, Quad, SPPS, FPPS, PPTS, and Forge Builder, which provide the engineering, manufacturing, integration, and pull-based logic that make the HPZ operable. The HPZ is the first physical step, but it is created by the system logic, not the other way around. 4. Strategic outcomes of the HPZ. The establishment of the HPZ delivers 4 immediate national outcomes. Air capacity, a measurable, expandable annual output of housing units. Air stability, a workforce and supply chain that operate continuously, not cyclically. Air quality, controlled manufacturing environments that eliminate the variability of site-based construction. Air speed, production and deployment timelines that compress from years to months. These outcomes are not theoretical. They are engineered into the zone's design. 5. The HPZ as the anchor for the future system. Everything that follows, EMBS, Quad, VEMAs, national deployment frameworks, industrial zones, and the full housing ecosystem, does not depend on the HPZ. Instead, the HPZ depends on these system frameworks to function. They provide the engineering rules, the manufacturing logic, the interoperability structure, the attribute layers, and the pull-based production strategy that make the HPZ capable of delivering industrialized housing output. Without these frameworks, the HPZ would have no engineering discipline, no manufacturing coherence, no system integration, no production logic, no national alignment. The HPZ is the turning point because it is the first physical commitment to an industrialized housing future, but it is enabled by the system, not the driver of it. The operational architecture of the housing production zone. The housing production zone is not simply a designated area for industrial activity. It is a fully engineered operational architecture designed to convert national housing demand into predictable, repeatable industrial output. This section explains how the HPZ functions as a living system, its internal logic, its operational flows, and the mechanisms that allow it to deliver continuous housing production at scale. 1. The HPZ as an integrated production ecosystem. The HPZ operates as a closed-loop industrial ecosystem, where every component, from raw materials to finished homes, is connected through controlled, synchronized processes. Its architecture is built around 4 interdependent layers: a production layer, factories, assembly lines, testing facilities, and precision manufacturing environments; a supply chain layer, material suppliers, component manufacturers, logistics hubs, and inventory systems; a regulatory layer, a unified authority governing standards, approvals, compliance, and certification; a workforce layer, training centers, skills pipelines, and stable employment structures. These layers do not operate independently. They are engineered to function as a single, coordinated system. 2. The flow of production inside the HPZ. The HPZ is designed around continuous flow, not project cycles. The operational sequence follows disciplined industrial logic. Demand intake. National housing requirements are translated into production schedules. Design standardization. Units are configured using pre-approved, interoperable design families. Material synchronization. Supply chains deliver materials just in time to minimize storage and waste. Manufacturing. Components are produced in controlled environments with precision tolerances. Assembly. Modules, panels, or volumetric units are assembled into complete housing systems. Quality assurance. Every unit undergoes industrial testing, certification, and compliance checks. Deployment. Finished units are transported to national deployment zones for installation. This flow is the operational backbone of the HPZ. 3. The regulatory engine of the HPZ. Traditional construction is slowed by fragmented regulation. The HPZ replaces this with a single regulatory engine that approves designs once, not repeatedly, certifies factories, not individual projects, enforces industrial standards, not site-by-site interpretations, integrates compliance directly into the production process. This shifts regulation from reactive inspection to proactive assurance. 4. Workforce architecture and skills pipeline. The HPZ requires a workforce that is stable, skilled, continuously trained, and aligned with industrial processes. To achieve this, the HPZ includes a technical academies for precision manufacturing skills, a certification pathways tied directly to production roles, a continuous upskilling programs aligned with technological evolution, a stable employment structures replacing transient labor models. The workforce is a strategic asset of the HPZ. 5. The HPZ as a national production asset. The HPZ is designed to operate for decades, not project cycles. It becomes a national production asset with a long-term capacity planning, expandable production lines, a modular factory growth, integrated logistics corridors, and national deployment coordination. This is the infrastructure that allows a country to produce housing at scale, year after year. The governance and management structure of the housing production zone. The housing production zone requires a governance structure fundamentally different from traditional construction oversight. Because the HPZ is a national production asset, its governance must reflect industrial discipline, regulatory coherence, and long-term operational stability. 1. The HPZ Governance Authority. At the center of the HPZ sits a single, dedicated governing body, the HPZ Authority. Its core functions include a strategic direction, setting long-term production targets aligned with national housing requirements, a regulatory integration, acting as the unified regulatory body for design approvals, compliance, and certification, operational oversight, ensuring factories, supply chains, and logistics operate within defined performance parameters, quality assurance, enforcing industrial standards across all production lines and processes, capacity planning, managing expansion, upgrades, and technological evolution within the zone. The HPZ Authority replaces fragmented, multi-agency oversight with a single point of accountability. 2. Governance principles. The HPZ governance model is built on 5 core principles. Integration, all regulatory, operational, and compliance functions unified under one authority. Predictability, fixed, transparent cycles for production schedules, approvals, and standards. Discipline, mandatory industrial processes enforced through continuous monitoring. Transparency, open reporting of performance metrics, output levels, and compliance data. Stability, governance insulated from short-term political or market fluctuations. 3. Internal structure of the HPZ Authority. The HPZ Authority is organized into 4 operational directorates: a production directorate, factories, assembly lines, and manufacturing performance; A regulatory directorate, design approvals, compliance, certification, and industrial standards. A supply chain and logistics directorate, material flows, inventory systems, and outbound deployment. A workforce and skills directorate, training centers, certification pathways, and workforce planning. Each directorate operates with clear mandates and measurable performance indicators. 4. Decision-making and accountability. The HPZ authority operates under a tiered decision-making model. A strategic decisions, national-level output targets, expansion plans, long-term investment. A operational decisions, production schedules, regulatory cycles, workforce planning. A technical decisions, engineering standards, testing protocols, quality assurance. Accountability is enforced through annual performance reviews, independent audits, transparent reporting to national government and stakeholders. 5. Relationship with national government. The HPZ authority operates at arm's length from central government but remains directly accountable for national housing output. Its relationship with government is defined by mandated output targets, annual and multi-year production requirements, funding agreements, long-term capital investment and operational budgets, regulatory mandates, authority to enforce industrial standards across the zone, performance reporting, regular updates on capacity, output, compliance, and workforce metrics. This structure ensures the HPZ is both empowered and accountable, with clear lines of responsibility. 6. Governance as a production enabler. The governance structure is not administrative overhead, it is a production enabler. It ensures factories operate at stable, predictable capacity, supply chains are synchronized and resilient, workforce pipelines remain continuous and skilled, standards are enforced consistently across all production lines, and output remains aligned with national housing needs. In this model, governance is not a constraint, it is the mechanism that makes industrialized housing production possible. Operational management inside the housing production zone. Operational management within the housing production zone is designed to ensure continuous, predictable, high-volume housing output. The HPZ functions as a fully integrated industrial ecosystem in which production, logistics, workforce, quality, and supply chain operations are synchronized under a unified operational model. This model is overseen by the HPZ operating company, which manages day-to-day operations while working within the strategic direction set by the HPZ authority. The objective is simple: stable flow, stable output, stable national supply. 1. Production flow management. The HPZ operates on a flow-based production model that prioritizes a continuous throughput, a minimized downtime, a predictable takt times, a synchronized workstations, a balanced production lines. Production is organized into modular streams, each capable of scaling independently. These streams are coordinated through a central production control function that monitors a real-time capacity, a bottlenecks, a material availability, a workforce allocation, a quality checkpoints. This ensures the HPZ maintains a steady, uninterrupted production rhythm, regardless of external market fluctuations. 2. Supply chain coordination. The HPZ integrates suppliers directly into the zone's operational fabric. Supply chain management focuses on inbound material flow, a just-in-time delivery, inventory minimization, a supplier performance monitoring, logistics synchronization. Suppliers operate under the HPZ participation framework, ensuring interoperability, compliance, predictable delivery performance. This creates a closed-loop supply chain in which materials, components, and assemblies move seamlessly through the zone. 3. Quality assurance and compliance operations. Quality assurance is embedded at every stage of production. The HPZ uses a multi-layered QA model that includes inline inspections, a digital traceability, a structural and safety verification, a compliance with national housing standards, export-ready certification. This is one of the key operational layers that will later connect directly to EMBS Quad. The HPZ cannot function without a unified quality and compliance system, and this is where those frameworks re-enter the narrative. 4. Workforce operations and shift management. The HPZ operates on a multi-shift model designed to maximize uptime and maintain continuous flow. Workforce operations include a shift scheduling, a skills allocation, a safety management, a training and certification, a performance monitoring. The workforce is treated as a strategic asset, supported by a technical colleges, a training centers, apprenticeship programs, upskilling pathways. This ensures the HPZ maintains a stable, skilled, and scalable labor force capable of supporting industrial-scale housing production. 5. Maintenance and asset management. Operational continuity depends on rigorous maintenance practices. The HPZ uses a predictive maintenance, a scheduled servicing, a asset lifecycle management, or equipment performance monitoring. Critical assets, such as automated lines, cranes, robotics, and logistics systems, are managed through a centralized maintenance control system that ensures a minimal downtime, extended asset life, a consistent production performance. 6. Monitoring, data, and operational intelligence. The HPZ operates on a data-driven model. Operational intelligence includes a real-time dashboards, a production analytics, a supply chain visibility, a workforce performance metrics, air quality and compliance data, a predictive forecasting. This data layer is essential for the later integration of a forge builder. The operational intelligence layer forms the foundation for system-level optimization. 7. Safety, risk, and contingency management. Safety is embedded into every operational layer. The HPZ maintains industrial safety protocols, emergency response plans, risk assessments, environmental controls, compliance audits. Contingency planning ensures the HPZ can maintain production even under supply disruptions, workforce shortages, equipment failures, external shocks. This resilience is a defining characteristic of the HPZ as a national asset. 8. Operational integration, preparing for the system layer. This section sets the stage for the next major step in the book, introducing the system that makes the HPZ operable. The HPZ provides the physical environment, the governance structure, the operational machinery. But no HPZ can function without a unified engineering to manufacturing to fielding system. This is where we will reintroduce ENBS, EMBS, Quad, SPPS, FPPS, PPTS, Forge Builder. These frameworks form the operational backbone that enables the HPZ to deliver consistent, interoperable, scalable housing output. Workforce operations and shift management. The workforce inside the housing production zone is managed as a strategic production asset, not a variable cost. Workforce operations are structured to ensure continuous flow, predictable output, and stable industrial performance across all production streams. The HPZ operating company oversees workforce planning, shift management, skills allocation, and safety, ensuring that labor capacity aligns with the zone's production targets and takt time requirements. The objective is to maintain a high-skill, high-stability, high-continuity workforce capable of supporting industrial-scale housing production. 1. Workforce structure and role definition. The HPZ workforce is organized into clearly defined operational groups. Production operators, workstations, assembly lines, fabrication technical specialists, welding, electrical, mechanical, digital fabrication quality inspectors, inline and end-of-line assurance material handlers and logistics staff, inbound, internal, outbound flow maintenance technicians, equipment uptime and predictive servicing supervisors and line leads, flow control, takt adherence, escalation training and safety officers, skills development and compliance. Each role is tied directly to production flow, ensuring staffing levels and skill profiles match operational demands. 2. Shift model and uptime maximization. The HPZ operates on a multi-shift model designed to maintain continuous production while protecting workforce well-being. Typical configurations include Air 2-shift model, extended daily production with handover overlap, a 3-shift model, full 24-hour operation for high-volume streams, a hybrid models, continuous operation on some lines, takt-aligned daytime shifts on others. Shift design is based on production demand, takt time requirements, equipment utilization, workforce availability, maintenance windows. The goal is to maximize uptime without overextending the workforce. 3. Skills allocation and competency management. Workforce allocation is competency-based, ensuring each workstation is staffed by trained personnel. Critical skills are always available. Multi-skilled operators can flex across lines. Supervisors maintain oversight of skill distribution. The HPZ maintains a skills matrix tracking qualifications, certifications, workstation proficiency, cross-training status, safety compliance. This matrix is used daily to allocate labor and ensure every shift is fully capable of meeting output targets. 4. Training, upskilling, and workforce pipelines. The HPZ includes a dedicated training and development function responsible for A onboarding, a technical skills training, a workstation certification, a safety training, a continuous upskilling, a leadership development. Training is delivered through on-site training centers, technical colleges, apprenticeship programs, manufacturer-led specialist training, digital learning platforms. This ensures a continuous pipeline of skilled labor, reducing dependency on external markets and protecting production stability. 5. Workforce safety and industrial culture. Safety is embedded into every aspect of workforce operations. The HPZ maintains a mandatory safety induction, a daily toolbox talks, a workstation-specific safety protocols, a PPE compliance, a incident reporting and investigation, a continuous safety improvement programs. The HPZ promotes an industrial culture built on a discipline, a predictability, a professionalism, a respect for process, a pride in production. This culture is essential for maintaining flow, quality, and workforce retention. 6. Performance monitoring and workforce analytics. Workforce performance is monitored through a attendance and punctuality, a workstation productivity, a takt time adherence, a quality performance, a safety compliance, a cross-training progression. Operational intelligence systems provide supervisors with real-time visibility of a staffing levels, a skill availability, a shift performance, a labor-related bottlenecks. This data supports proactive decision-making and ensures alignment with production requirements. 7. Workforce stability as a national asset. The HPZ workforce is treated as a national capability, not a temporary labor pool. This approach ensures a long-term employment stability, a predictable career pathways, a reduced turnover, a higher skill retention, a stronger industrial culture. A stable workforce is essential for a consistent production, a quality assurance, a safety performance, a international competitiveness. This stability is one of the defining strengths of the HPZ model. 8. Workforce operations as the foundation for system integration. This section prepares the ground for the reintroduction of ENBS Quad as the system that makes the HPZ operable. Workforce operations depend on a standardized engineering rules, ENBS a standardized manufacturing logic, EMBS a system-wide integration, Quad a attribute layers, SPPS, FPPS, PPTS a pull-based production, Forge builder. The HPZ provides the workforce. The system provides the method. Together, they deliver national-scale housing production. Maintenance and asset management. Maintenance and asset management within the housing production zone are designed to ensure uninterrupted production, long-term equipment reliability, and predictable operational performance. The HPZ operates as a high-intensity industrial environment where uptime is a national priority and asset failure has direct implications for housing supply, export capability, and national productivity. The HPZ operating company manages all maintenance and asset functions through a structured, data-driven model integrating predictive analytics, scheduled servicing, and lifecycle planning. 1. Asset classification and criticality. All assets within the HPZ are classified according to operational importance. Primary production assets, automated lines, fabrication equipment, robotics, heavy machinery as secondary production assets, jigs, fixtures, assembly rigs, material handling systems are infrastructure assets, power systems, utilities, cranes, internal logistics routes are digital assets, control systems, sensors, operational intelligence platforms are safety and compliance assets, fire systems, environmental controls, monitoring equipment. Each asset class has defined maintenance requirements, inspection cycles, and performance thresholds. 2. Predictive and preventive maintenance. The HPZ uses a dual maintenance model. A predictive maintenance, sensors, telemetry, and operational data to anticipate failures, a preventive maintenance, scheduled servicing based on hours, cycles, and specifications. This ensures a reduced downtime, extended asset life, stable production flow, a lower long-term maintenance costs. Predictive maintenance is especially critical for high-value assets such as automated lines and robotics, where unplanned downtime disrupts takt time and output. 3. Maintenance planning and scheduling. Maintenance activities are planned around production requirements to avoid disrupting flow. This includes a scheduled maintenance windows, a shift-aligned servicing, a night shift interventions for high-impact assets, a coordinated shutdowns for major upgrades. Maintenance planning is integrated with a production schedules, a workforce availability, a supply chain timing, a quality assurance cycles. This ensures maintenance supports, rather than interrupts, production. 4. Asset lifecycle management. Every asset in the HPZ is managed through a defined lifecycle model. Acquisition, commissioning, operational use, maintenance, upgrades, decommissioning. Lifecycle management ensures technological currency, performance within specification, predictable replacement cycles, stable capital planning. The HPZ status as a national asset enables long-term lifecycle planning rather than reactive replacement. 5. Spare parts, inventory, and technical support. The HPZ maintains a structured spare parts strategy. Critical spares held on-site, high-usage consumables stocked in controlled quantities, supplier-managed inventory for specialist components, rapid response technical support agreements. This ensures rapid response to equipment failures, a component where unexpected breakdowns. It also reduces dependency on external supply chains for time-critical parts. 6. Asset performance monitoring. All major assets are monitored through a centralized operational intelligence system tracking utilization, cycle times, energy consumption, vibration and temperature data, error codes, maintenance history. This data supports predictive maintenance, performance optimization, root cause analysis, upgrade planning. It also forms part of the HPZ's compliance and reporting framework. 7. Compliance, safety, and regulatory maintenance. Maintenance activities align with national safety regulations, building code requirements, environmental standards, industrial licensing conditions. This includes mandatory inspections, certification renewals, safety system testing, environmental monitoring. Compliance maintenance ensures the HPZ remains fully operational and legally protected. 8. Asset management as a foundation for system integration. This section prepares the ground for the reintroduction of ENBS Quad as the system that makes the HPZ operable. Maintenance and asset management depend on standardized engineering rules, ENBS standardized manufacturing logic, ENBS system-wide integration, Quad attribute layers, SPPS, FPPS, PPTS pull-based production, Forge Builder. The HPZ provides the physical assets. The system provides the operational logic. Together, they deliver national-scale, reliable, industrial housing production. Monitoring, data, and operational intelligence. Operational intelligence within the housing production zone provides the visibility, control, and analytical capability required to maintain stable, high-volume production. The HPZ operates as a data-driven industrial ecosystem, where every production stream, asset, workforce unit, and supply chain interface is monitored in real time. This ensures the HPZ remains predictable, efficient, and resilient, characteristics essential for a national-level housing production asset. The HPZ operating company manages the operational intelligence layer, integrating data from engineering, manufacturing, logistics, quality, and workforce systems into a unified decision support environment. 1. Real-time production monitoring. The HPZ uses real-time monitoring systems to track a production throughput, a takt time adherence, a workstation performance, a bottleneck formation, a material flow, a quality checkpoints. This visibility allows supervisors and managers to adjust staffing, rebalance lines, escalate issues, maintain flow stability. Real-time monitoring is essential for protecting the HPZ's output targets and ensuring predictable national supply. 2. Supply chain visibility and material intelligence. The HPZ integrates supply chain data into its operational intelligence platform, providing visibility over inbound materials, supplier performance, inventory levels, logistics timing, internal material movement, outbound dispatch. This ensures that materials arrive when needed, inventory remains controlled, production lines remain fed, export schedules remain predictable. Supply chain intelligence is one of the HPZ's core resilience mechanisms. 3. Workforce analytics and performance insight. Workforce data is monitored to ensure alignment between labor capacity and production demand. This includes attendance and punctuality, skills availability, workstation proficiency, shift performance, safety compliance, cross-training progression. Workforce analytics support. Shift planning, skills allocation, training prioritization, performance improvement. This ensures the HPZ maintains a stable, capable, and responsive workforce. 4. Quality and compliance data. Quality assurance is fully integrated into the HPZ's data environment. The system tracks inspection results, defect rates, rework levels, structural compliance, safety certification, export-ready documentation. This data is essential for maintaining national housing standards, ensuring international trade compatibility, supporting regulatory audits, enabling continuous improvement. This is also one of the key points where ENBS and EMBS will later re-enter the narrative, because quality and compliance depend on unified engineering and manufacturing rules. 5. Asset performance and predictive analytics. Operational intelligence includes continuous monitoring of equipment utilization, cycle times, energy consumption, vibration and temperature, error codes, maintenance history. Predictive analytics identify emerging failures, performance degradation, maintenance requirements, upgrade opportunities. This ensures the HPZ maintains high uptime and stable production flow. 6. Environmental and safety monitoring. The HPZ monitors environmental and safety conditions across the zone, including air quality, noise levels, temperature and humidity, hazardous material controls, fire safety systems, emergency response readiness. This ensures compliance with national regulations and protects workforce well-being. 7. Integrated operational dashboards. All operational data is consolidated into integrated dashboards that provide a real-time status, trend analysis, predictive forecasts, performance comparisons, risk indicators, decision support insights. Dashboards are used by supervisors, production managers, quality teams, maintenance teams, HPZ OPCO leadership, HPZA oversight bodies. This ensures decision-making is consistent, informed, and aligned with national objectives. 8. Operational intelligence as the bridge to system integration. This section prepares the ground for the next major step in the book, introducing the system that makes the HPZ operable. Operational intelligence depends on standardized engineering rules, ENBS standardized manufacturing logic, EMBS system-wide integration, quad attribute layers, SPPS, FPPS, PPTS pull-based production, forge builder. The HPZ provides the data. The system provides the logic. Together, they create a national-scale, intelligent, industrial housing ecosystem. Safety, risk, and contingency management. Safety, risk, and contingency management within the housing production zone form the protective framework that ensures uninterrupted production, workforce well-being, and national resilience. The HPZ operates as a high-intensity industrial environment where safety is engineered into every process, risk is continuously monitored, and contingency plans are designed to maintain output even under adverse conditions. The HPZ operating company manages this framework through structured protocols, real-time monitoring, and coordinated response mechanisms that align with national regulations and international standards. 1. Industrial Safety Framework. The HPZ maintains a comprehensive industrial safety framework that includes a mandatory safety induction for all personnel, workstation-specific safety protocols, PPE requirements and compliance checks, daily toolbox talks and shift briefings, incident reporting and investigation procedures, continuous safety improvement programs. Safety is treated as a non-negotiable operational requirement, not an administrative obligation. 2. Hazard identification and risk assessment. Risk assessment is embedded into every operational layer. The HPZ conducts a routine hazard identification, task-specific risk assessments, equipment-specific risk evaluations, environmental risk monitoring, periodic zone-wide risk audits. These assessments ensure that risks are identified early, mitigated effectively, and monitored continuously. 3. Emergency preparedness and response. The HPZ maintains a structured emergency response capability that includes trained emergency response teams, fire safety systems and suppression equipment, evacuation routes and muster points, hazardous material handling protocols, medical response capability, coordination with local emergency services. Regular drills ensure all personnel understand their roles and responsibilities during an emergency. 4. Environmental safety and compliance. Environmental controls are integrated into HPZ operations to ensure compliance with national regulations and protect workforce well-being. This includes monitoring of air quality and noise levels, temperature and humidity, waste management, emissions and discharge, hazardous material storage. Environmental safety is treated as part of the HPZ's operational integrity. 5. Business continuity and production resilience. The HPZ maintains a comprehensive business continuity framework designed to protect production flow during supply chain disruptions, workforce shortages, equipment failures, power or utility interruptions, external shocks, economic, environmental, or geopolitical. Continuity measures include alternative supply routes, cross-trained workforce pools, redundant critical assets, backup power systems, emergency production plans. This ensures the HPZ can maintain output even under adverse conditions. 6. cybersecurity and digital risk management. As a data-driven industrial ecosystem, the HPZ includes robust cybersecurity measures to protect our operational intelligence systems, our production control systems, our supply chain data, our workforce information, our compliance records. Cybersecurity protocols include our access controls, our network segmentation, our intrusion detection, our data encryption, our incident response plans. Digital resilience is essential for protecting the HPZ's operational continuity. 7. Regulatory compliance and oversight. Safety and risk management are aligned with our national industrial safety regulations, our building code requirements, our environmental standards, our international trade compliance, our HPZA oversight protocols. Compliance is monitored through our audits, our inspections, our certification renewals, our performance reporting. This ensures the HPZ remains legally protected and operationally stable. 8. Safety and risk management as the foundation for system integration. This section prepares the ground for the next major step in the book, introducing the system that makes the HPZ operable. Safety, risk, and contingency management depend on a standardized engineering rules, ENBS, a standardized manufacturing logic, EMBS, a system-wide integration, quad attribute layers, SPPS, FPPS, PPTS, a pull-based production, forge builder. The HPZ provides the environment. The system provides the method. Together, they create a resilient, safe, and predictable national housing production capability. Operational integration, preparing for the system layer. Operational integration within the housing production zone is the point where all operational functions, production, workforce, maintenance, logistics, quality, and data, converge into a single, coherent industrial environment. While each operational layer can function independently, the HPZ only becomes a true national-scale production asset when these layers are synchronized through a unified system architecture. This section defines the integration logic that prepares the HPZ for the system layer that follows, the engineering, manufacturing, and deployment system introduced through ENBS, EMBS, and Quad. 1. Integration across production streams. The HPZ contains multiple production streams, each capable of operating at different takt times and volumes. Operational integration ensures that these streams share common engineering rules, follow consistent manufacturing logic, operate within the same quality envelope, synchronized material flow, align with shared logistics routes. This prevents fragmentation and ensures the HPZ behaves as one industrial system, not a collection of independent factories. 2. Integration of workforce and production flow. Workforce operations are integrated with production requirements through a skills-based allocation, a shift alignment with takt time, a cross-training to support flow stability, a real-time workforce visibility. This ensures labor capacity and production demand remain synchronized, protecting throughput and preventing bottlenecks. 3. Integration of maintenance and asset performance. Maintenance operations are integrated with production schedules and asset performance data to ensure a predictive maintenance aligns with takt servicing windows do not disrupt flow, critical assets receive priority attention, a life cycle planning supports long-term capacity. This integration is essential for maintaining the HPZ's uptime and reliability. 4. Integration of supply chain and logistics. Supply chain operations are integrated with production and dispatch through a real-time material visibility, a synchronized inbound and outbound logistics, a supplier performance monitoring, a inventory control aligned with takt. This ensures materials arrive when needed and finished units leave the zone predictably. 5. Integration of quality and compliance. Quality assurance is integrated across all production streams through a shared inspection standards, a unified compliance rules, a digital traceability, a consistent certification processes. This is one of the most important integration points, because it directly prepares the HPZ for the system layer. Quality and compliance cannot be integrated without unified engineering and manufacturing rules, which is where ENBS and EMBS enter the architecture. 6. Integration of data and operational intelligence. Operational intelligence integrates data from a production, a workforce, a maintenance, a supply chain, a quality, a safety, environmental monitoring. This creates a single operational picture that supports a decision-making, a forecasting, a risk management, a performance optimization. This data layer is the foundation for the system layer that follows. 7. Integration through interfaces. Operational integration is achieved through 4 interface types. A product interfaces, how components, assemblies, and modules connect to process interfaces, how production steps align and hand over digital interfaces, how data flows across systems are organizational interfaces, how teams coordinate and escalate. These interfaces are the connective tissue of the HPZ. They are also the exact same interface types that Quad uses, which is why this section is the perfect bridge to the system layer. 8. Why the HPZ cannot operate without a system layer. This is the key message that prepares the reader for the next chapter. The HPZ provides the physical environment, the governance structure, the operational machinery, the workforce, the data. But none of this works at national scale without a unified engineering to manufacturing to fielding system. This is where the system layer enters. ENBS, National Engineering and Manufacturing Rules EMBS, the sector definition Quad, the operational engine SPPS, FPPS, PPTS, the attribute layers Forge Builder, the pool-based production strategy. The HPZ is the zone. The system is the engine. Operational integration is the bridge between them. The Quad delivery conduit, how projects flow from the zone to the Forge Builder. 1. Quad is the national delivery capability, not a modular system. Quad is not a modular product, a factory model, or a proprietary construction method. It is a national delivery capability that enables housing projects to be delivered at scale through a structured, predictable conduit. SPPS, MPPS, Zone, PPDSS, Forge Builder. This conduit is what turns the zone from a geographic designation into a functioning national housing engine. Modular systems cannot do this because modular factories are vertical silos. Quad works because it is a horizontal system. 2. Why modular cannot scale, and why Quad can. Modular factories attempt to do everything inside one building. A design, a engineering, a certification, a manufacturing, a delivery, a installation. This creates a closed loop that collapses under scale. Every project forces redesign, every redesign forces re-engineering, every re-engineering forces retooling, every retooling stops production, every stop destroys unit economics. This is why modular factories rarely exceed 200 to 400 homes per year, even with heavy capital investment. Modular builds projects. Quad builds products, processes, and national capability. That is the essential distinction. 3. SPPS, the foundation that makes Quad work. SPPS is not a standard product. It is a system of standardized components engineered to produce rigid, repeatable product envelopes. SPPS is designed from end use backwards, for manufacturing optimization, for containerized global transport, for microfactory assembly, for predictable cost and predictable delivery. This removes the redesign-retooling cycle that cripples modular factories. SPPS creates predictable unit economics, the first step in the micro-to-macro economic chain. 4. MPPS. Manufacturers produce products, not projects. Under Quad, manufacturers do not redesign or re-engineer for each project. They produce SPPS-compliant products that are pre-approved, repeatable, containerized, globally manufacturable. This creates a continuous production, stable unit costs, scalable output. This is the second economic layer, production economics. 5. The zone, the conduit, not the innovation. The zone is not the innovation. The zone is the platform that allows Quad to operate at national scale. The zone provides a land, planning alignment, infrastructure, a workforce access, a regional economic uplift. But the zone only works because Quad provides the capability that flows through it. Without Quad, a zone is just land. With Quad, a zone becomes a national housing engine. 6. PPDSS, turning products into predictable assembly. PPDSS is the controlled microfactory environment where SPPS products are assembled. It provides a defined sequencing, a defined tolerances, a defined logistics, a defined inspection points, a defined assembly flow. This transforms construction into industrialized assembly, enabling thousands of SMEs to become forge builders. This is the third economic layer, assembly economics. 7. The Forge Builder, the national delivery class. The Forge Builder is not a modular installer. They are the national assembly workforce that turns Quad capability into national output. Forge Builders assemble SPPS products, operate within PPDSS microfactories, deliver predictable outcomes, create national employment, scale output beyond any modular factory. This is the fourth economic layer, employment economics. 8. Why Quad works and modular does not, in one sentence. Modular factories collapse under redesign and retooling. Quad removes redesign and retooling entirely. That is the whole point. 9. The direct lead into micro-macro economics. This section sets up the economics chapter because Quad creates a predictable unit economics, SPPS a continuous production economics, MPPS a predictable assembly economics, PPDSS a national employment economics, Forge a regional uplift economics, Zone a national GDP and GNI growth, Quad as capability. This is the natural bridge into the next chapter. Micro and macro economic impact of Quad. 1. Overview, housing as a national economic engine. Quad reframes housing delivery from a cost center into a national economic engine. It does this by shifting the system from a project-based construction to volume-based industrial activity, a domestic dependency to international capability exchange, a labor scarcity to vocational expansion and skills renewal. This section sets out how Quad generates economic impact at both the micro and macro levels, and why only a few nations can operate in isolation. The UK cannot meet its housing volume requirements without integrating into global supply networks. Microeconomic impact. 2. Employment creation and workforce expansion. The Quad system expands employment by distributing activity across thousands of SMEs through the Forge Builder model. Key microeconomic outcomes. Job creation across all regions, not just manufacturing hubs, are stable, year-round employment due to continuous production, a higher productivity per worker through industrialized assembly, a reduced dependency on declining traditional trades. This transforms the zone from a cost burden into a net tax generator. 3. Vocational training and skills renewal. The zone becomes a national vocational conduit, directly linked to universities, technical colleges, apprenticeship programs, modern construction training pathways. Traditional construction skills are declining and misaligned with industrialized methods. Quad replaces this with training in assembly, not artisanal craft, training in digital tools, not legacy trade techniques, training in industrial processes, not site improvisation. This raises intellectual capital, increases employment elasticity, and creates a future-ready workforce. 4. Local economic multipliers. Every zone generates a local spending, a local supply chain activity, a local SME participation, a local tax uplift. This is the foundation of microeconomic uplift. Jobs, wages, consumption, taxation, reinvestment. Macroeconomic impact. 5. The volume reality. Few nations can deliver alone. This is the critical ministerial message. Even with zones, the UK cannot meet its housing volume requirements alone. Reasons. Insufficient domestic labour, insufficient domestic manufacturing throughput, insufficient access to materials, insufficient time to scale domestic capacity. China could meet its own volume. The UK cannot, not within required timelines. This is not a weakness. It is the economic logic of globalized industrial systems. 6. Quad as an international volume hub. By removing the redesign retooling cycle through SPPS and MPPS, Quad enables international component inflow, a domestic assembly at scale, export of specialized UK capabilities, balanced trade relationships. The zone becomes a national asset that plugs into global supply chains, not a closed domestic silo. 7. Global accessibility to materials and components. The unspoken truth in housing delivery is now explicit. Volume depends on access to global materials and components. Quad formalizes this through containerized SPPS components, international MPPS manufacturing partners, cross-border product harmonization, predictable logistics and lead times. This ensures the UK can meet its housing targets without overloading domestic capacity. 8. Specialization exchange. What the UK gives back. The UK may not specialize in high-volume manufacturing, but it can specialize in high-value engineering, digital construction technologies, regulatory frameworks, quality assurance systems, industrialized assembly expertise, zone governance models. This creates a two-way economic flow. A volume in, components, materials, value out, expertise, governance, digital systems, high-value services. This is the core of the macroeconomic engine. 9. Zones as national and international economic assets. The zone becomes a national priority for housing delivery, a regional economic accelerator, an international hub for volume balancing, a center for vocational and industrial training, a platform for global collaboration. This dual identity, national asset plus international hub, is what makes Quad economically transformative. 10. Summary. The micro-macro economic ladder. Quad creates a structured economic ladder. A micro, jobs, skills, wages, taxation, local uplift. A macro, global supply, domestic assembly, specialization, exchange, national GDP and GNI growth. This is the economic logic that underpins the entire Quad system. GDP, GNI, and cross-border investment impact. A national industrialized housing program must be assessed not only through domestic production metrics but through its wider contribution to GDP, its effect on GNI, and its capacity to attract and retain international investment without eroding national value. Quad and the EMBS zone model provide a structured economic framework that meets these requirements with clarity and precision. GDP impact. The transition from fragmented construction to industrialized production converts housing into a measurable, multi-sector economic driver. Industrialized housing activates a manufacturing, logistics, a digital engineering, a compliance, a long-term asset services. Productivity rises as factories operate continuously, a learning curves compound, a rework is eliminated. Public expenditure yields a higher proportion of recorded economic activity, and national capacity expands without proportional increases in labor. GNI impact. Traditional construction models disperse value through imports, a foreign contracting, external financing. Quad reverses this pattern by anchoring a design, of engineering, or assurance, or assembly, a long-term services. Within the national economy, the zone becomes a mechanism for value retention, ensuring that the economic return generated by housing delivery remains within the country rather than leaking across borders. Cross-border investment impact. Quad's most distinctive feature is its structured cross-border investment capability. By separating design, assurance, manufacturing, and assembly into interoperable layers, Quad enables international participation while preserving national economic sovereignty. Example: a Chinese investor may invest in a UK housing program while keeping the manufacturing component, and therefore the economic return, within China. As the UK gains volume, delivery, and domestic uplift, China retains manufacturing value and investment return. Both nations benefit without compromising control of their respective economic positions. This is not offshoring. It is a rules-based system for aligning value across borders. It enables a collaboration, a sovereignty, a mutual economic uplift. It also provides developing nations with a viable route into global housing programs, enabling them to participate at scale while keeping their share of value at home. A national industrialized housing strategy is more than a domestic production system. It is a platform for international economic cooperation, a structure that enables nations to collaborate through shared standards, governance, digital assurance, and industrial frameworks. Through this approach, each participating nation strengthens its own economy while contributing to a transparent, rules-based global system. The result is a dual uplift. Domestic GDP and GNI rise through increased production and retained value. International partners gain access to a stable, reliable environment that protects investment and anchors profit within their own economies. Together, these mechanisms form a cooperative architecture, a system designed for balanced growth, shared prosperity, and sustainable industrial development. This completes the economic architecture of the program. International case studies application of EMBS zones and Quad-enabled assurance across 6 national contexts. National contexts: Case Study 1, United Kingdom, systemic fragmentation, policy drift, and the absence of industrialization. Context: the UK housing system has experienced decades of underdelivery, driven by fragmented supply chains, inconsistent policy cycles, and a construction sector heavily reliant on traditional, labor-intensive methods. Despite repeated government interventions, the system has remained structurally incapable of scaling output beyond 180 to 220,000 homes per year. Systemic failures: a fragmented delivery model with no national production capacity, a stop-start policy cycles preventing long-term investment, skill shortages, and an aging workforce, a low standardization, high variability, and limited repeatability, planning delays, and inconsistent local authority capability. No industrial zones dedicated to housing production. What Quad would have done: establish national housing production zones with integrated supply chains, introduce component standardization across regions, deploy EMBS to unify design, manufacturing, and assembly, create a predictable demand pipeline for 10 to 15 years, reduce reliance on traditional labor through industrialized workflows. Expected outcomes: a 30 to 40% increase in annual output, a 20 to 25% cost stabilization, a reduced planning to delivery cycle. Predictable national capacity for 250 to 300,000 homes per year.
Case Study 2, Singapore, a controlled, industrialist system with high repeatability, Context: Singapore's Housing and Development Board operates one of the world's most efficient housing delivery systems. Its success is rooted in industrialization, standardization, and long-term planning. Systemic strength: centralized authority with full control of land, planning, and delivery. High standardization of components and building types. Integrated supply chain with dedicated manufacturing capacity. Predictable demand pipeline. Strong digital integration. What Quad adds: even in a high-performing system, Quad strengthens cross-factory interoperability, component-level standardization across suppliers, resilience against supply chain shocks, scalable, exportable frameworks. For overseas partnerships, expected outcomes: increased resilience, lower long-term cost volatility, greater international replication potential.
Case Study 3. United States, scale without integration. A market too large to coordinate. Context: the United States has enormous construction capacity but lacks national coordination. The market is dominated by fragmented private actors, inconsistent state regulations, and a near-total absence of industrialis housing zones. Systemic failures: 50 regulatory regimes, no national standard, highly fragmented supply chains, minimal standardization, volatile labor markets, no unified industrial strategy. What Quad would done: introduce federal-level component standards, establish regional industrial housing zones, deploy EMBS to unify design-to-assembly workflows, create predictable procurement pipelines for states, reduce cost volatility through industrialis production. Expected outcomes: 30% reduction in delivery time, 15 to 20% cost stabilization, scalable capacity for disaster response housing, stronger resilience across states.
Case Study 4. Australia, high costs, low productivity, and geographic fragmentation. Context: Australia faces high construction costs, long supply chains, and a geographically dispersed population. Productivity has stagnated for decades, and industrialization remains limited. Systemic failures are long-distance logistics, a high labor costs, a low standardization, a fragmented state-level regulations, a minimal industrial capacity. What Quad would have done are establish state-based industrial housing hubs, a standardized components across states, a deploy EMBS to reduce labor dependency, a shorten supply chains through regionalized production. Expected outcomes: 20 to 25% reduction in logistics overhead, a faster delivery cycles, increased resilience to labor shortages.
Case Study 5. India, scale potential without industrial discipline. Context: India has massive demand and a large labor pool, but the housing sector remains dominated by traditional construction, inconsistent quality, and limited industrialization. Systemic failures: low standardization, a high variability in quality, fragmented supply chains, a limited mechanization, and unpredictable delivery cycles. What Quad would have done: introduce national component standards, establish industrial housing corridors, deploy EMBS to unify design and production, reduce variability through repeatable manufacturing. Expected outcomes: improved quality consistency, faster delivery at scale, or stronger export potential for Indian manufacturers.
China, opportunity through manufacturing capacity. China holds a unique opportunity to contribute to the global housing system through its vast manufacturing capability. Under a framework such as SPPS, this capacity can support the globalization of housing stock, not by leading or dictating, but by enabling nations to access high-volume, standardized components that align with their own national systems. It represents a cooperative model where industrial strength serves shared progress, allowing each country to maintain sovereignty while benefiting from China's scale and precision. In this way, China's role becomes one of supportive participation, reinforcing the principle that Quad and its allied systems remain national first, globally connected. Final global synthesis. The global synthesis marks the moment where national innovation meets shared purpose. Each system, Singapore, the United States, Australia, India, and China, stands distinct, sovereign, and self-defined. Yet together, they form a connected architecture of industrial capability, digital assurance, and economic cooperation. Under frameworks such as Quad and SPPS, nations retain control of their housing systems while participating in a wider exchange of standards and production logic. This is not globalization by ownership, it is globalization by interoperability. Singapore demonstrates precision and repeatability. The United States shows resilience and scalability. Australia delivers logistics and regional efficiency. India transforms its workforce through skill and certification. And China holds the opportunity to support global housing stock through manufacturing capacity, reinforcing, not replacing, national autonomy. Together, these systems form a global economic engine, national first, globally connected. A structure where industrial logic, digital assurance, and human capability align to create a sustainable, equitable housing future for all. Closing reflection. As we reach the end of this journey, one truth becomes clear. The future of housing is not defined by a single nation, a single model, or a single ideology. It is defined by the ability of each country to strengthen its own system while connecting to a wider ecosystem of capability, standards, and shared learning. Industrialized housing is not a technology story. It is a story of sovereignty, of national confidence, and of the quiet power that comes from systems built with intention. The frameworks explored in this work, Quad, SPPS, and the wider family of interoperable models, show that nations can modernize without surrendering identity and collaborate without compromising control. What emerges is a new kind of global architecture, one where countries remain firmly in charge of their own housing futures, yet benefit from the scale, precision, and predictability that only shared standards can unlock. This is the balance we must hold. National first, globally connected. And as the world continues to urbanize, industrialize, and digitize, the systems we build today will shape the opportunities of tomorrow. Thank you for listening, and for stepping into this vision of what housing can become when nations choose clarity, capability, and cooperation. As we conclude, a word about the author. Carl Dickson was born close to the historic Rochdale Cooperative Building, the birthplace of modern collaboration. That early connection to cooperative thinking would later shape a career focused on practical, engineered solutions that help industries work together rather than operate in isolation. As a systems architect and industry practitioner, Dickson specializes in engineered manufacturing and industrialized construction, with a strong emphasis on technologies that can be deployed directly on real projects. His work centers on design-through-manufacture systems that translate cleanly into on-site execution, ensuring that innovation is measured by what can actually be delivered. Dickson's contribution is not in policy, zoning, or legislative design, but in the commercially applicable technologies that help convert the off-site construction sector from a fragmented, siloed market into a coordinated, cooperative, globally aligned ecosystem. These technologies are effective on a project-by-project basis, enabling immediate practical value, while also being scalable enough to support national-level solutions where required. His approach emphasizes interoperability, manufacturability, and the engineering logic needed to modernize how building products are conceived, produced, and delivered. In this sense, the cooperative spirit of Rochdale continues through his work, not as an ideal, but as a practical pathway for industries seeking to collaborate at scale.